Hello, everyone. Welcome to the TMLS annual conference. My name is Aarti Malhotra, PhD student at University of Waterloo, and I'm glad to be the moderator for today's session. I'm honored to introduce Dr. Robert Monarch. Dr. Robert has a PhD from Stanford University. He's an expert in combining human and machine intelligence, working with ML approaches to text, speech, image, and video processing. Dr. Robert has founded several AI companies, building some of the top teams in AI. He has worked in many diverse environments across the globe, in organizations ranging from startups to the United Nations. He has shipped machine learning products as startups at Amazon, Apple, Google, IBM, and Microsoft. He has published more than 50 papers on AI and is a regular speaker about technology in an increasingly connected world. Dr. Robert is the author of Human in the Loop machine learning book as well. May I now request Dr. Robert to present unsolved problems in human in the loop machine learning. If anyone has any question, please feel free to post in the chat. We'll have a Q&A session after the talk. Over to you, Dr. Robert.
Thanks, Adi. I appreciate the introduction, and it's great to be here today. I'm coming to you from San Francisco, so I'm actually at the start of my day here. Please excuse me drinking coffee while I while I give this presentation, and I'll invite questions at any time during this talk. Like Adi said in the introduction, I'm the author of Human in the Loop machine learning, and in particular today, I want to focus on what I think are some of the most interesting unsolved problems in ways that we combine human and machine intelligence. I guess to frame the book, this is the book I wish existed when I began my career in data science. In academia, we get taught how to build algorithms, and there isn't really much of a focus on data. But I'm sure a lot of you have the experience in industry that you spend more time thinking about the data side of the problems than you do thinking about the algorithms. And the set of methods that we use for quality control and data sampling are just as mathematically complex and interesting as those that we use in machine learning and the algorithms themselves. They're just not as widely known. And I think this is really a point of contention. So Chris Menin, who is the head of the AI lab at Stanford and was my PhD advisor, writes this in the forward to the book, where it's an open secret. It's well known that the right annotations are often more important than the latest state-of-the-art algorithm. So that is what motivated me to write this book, so we can put some of these best practices into one place and have that as a good resource, especially for people starting out as data scientists. But today in particular, I want to focus on the things that aren't solved. So 90% of the book is about the basics and some deep dives into some specific use cases. And some of the most interesting things I found when writing the book was that, wow, like there were some really just basic things in machine learning, especially on the data side, that we haven't solved. And I would like to bring these to more people's attention, because I think they all deserve some more smart people thinking about ways to solve them. So to frame the talk, here is a really high-level diagram of what a typical deployed machine learning system looks like. So you'll have a deployed machine learning model. In this case, let's assume it's a labeling task. You will sample items, unlabeled items for human review, and this is known as active learning. And typically using the model itself, or at least part of the sampling strategy. The annotation process is where humans provide feedback and labels, and you run quality control on that process in order to create your training data. And then in most machine learning models today, you use some kind of representation or transfer learning. And so all of these will be relevant for the talk today, because the unsolved problems draw on one or more of each of these. And I'll start with active learning. So the most common method in active learning, or set of methods, are known as uncertainty sampling. So in this very simple binary classification task, this is sampling items near the decision boundary, because these items are the most likely to be misclassified by the model today, so that when they get a correct human label later, they're the most likely to result in a change in a more accurate decision boundary. And there's a few different ways that we commonly measure uncertainty in data sampling. So let's assume we have a full class classification problem like this PyTorch tensor here, where our most confidently classified item is, second one here is classified with 64% confidence. So the most common way that I'm sure you've used to calculate your confidence, or rather your uncertainty in the prediction, is to look at the difference between the most confident item and 100% confidence. And then we just apply n-1 as a denominator as a normalizing factor. So this gives us a scale of 0 to 1, where 1 is the most uncertain. And you might have also used margin of confidence. So margin of confidence is the difference between the top two most confident predictions. Similar to margin of confidence, the ratio of confidence is the ratio between the top two most confident predictions. It's actually more mathematically well motivated than margin of confidence, where we take the difference. So for example, if you train a model using mean squared error, this objective function, the ratio between the top two most confident predictions should reflect the model's interpretation of the frequency, the ratio of the frequency in the training data. So if this ratio is 50%, then one of the items is 50% more common. However, for historical reasons, most people use margin confidence rather than ratio of confidence. Finally, entropy is the difference between all predictions as defined by information theory. So the difference between the actual probability distribution and one, which in this case would be all at 25%. And it's important to think about how you design your uncertainty sampling system, because these different metrics will sample very different areas for uncertainty. So here's an example you can play with yourself on my website. Click around, and then each of these black dots represent a different class. So you can see here on the left-hand side, where we have a 3-class problem, that for margin of confidence and ratio of confidence, it's this pairwise confusion. So we're looking at the top two most confident. It's a pairwise confusion, which is where we would sample the most. So the most heat is where we would sample the most. Whereas entropy, which looks at overall confusion, is therefore looking for the most confusion space, which is right in the middle here. And when we look at more complicated boundaries, like on the right-hand side, we can see that where the different algorithms will sample are really different parts of our confusion space. So simply deciding what type of confusion is the best for your particular task will have a big influence on what you sample for human review. And then just to highlight, I think, some really interesting recent research on ensemble models. So for a long time, ensemble models have been a method for uncertainty sampling too, where you will get multiple predictions for the same item across different models, maybe varying by features or by data or both. And then you'd look both at the average uncertainty across those predictions as well as the variation. So the level of average uncertainty and the level of variation are both good indications that you might want to sample this for human review. And some of the more interesting variations have been in using dropouts in a single model at prediction time. So I'm sure you've all used models in training time as one method to help avoid overfitting your model to particular data. If you do the same at inference time, so taking the same item through the same model but with different random dropouts, then you get the same effect as from an ensemble model. You can look at the average uncertainty and the overall variation, both of which have been shown to be correlated with items that are more valuable for humans to review. And one thing which is unsolved here is variation in uncertainty based on softmax space or equivalent temperature. So let's assume that all our outputs are softmax, and we have two items 1 and 2, and the logics, which are the input to softmax, are what you can see in the top left here. Depending on the base, or equivalently the temperature of softmax, this would be the log base or the temperature applied, which of these items is ranked as the most uncertain will actually depend on that base or temperature. So at lower bases, which would be higher temperatures, at lower bases, item 2 is more confident, whereas at higher bases, item 1 is more confident. So if you have a sampling strategy where you're looking for the most uncertain, the choice of base, which is completely arbitrary, or temperature, it won't change your prediction within an item. So it's not going to change that label A is the most confident in both cases. However, it will change whether item 1 or 2 is the most uncertain. Before I wrote the book, people actually said that this wasn't true, that this was invariable, including a Turing Award winner who got angry with me on Twitter about it. But looking at, especially at the uncertainty side of a lot of popular data sets, you get a lot of variation here. So this temperature or base is therefore another variable that we can look at and optimize for to get better samples, but there's not a single paper that looks at it right now. I think that's pretty crazy too when you think about how popular softmax is, and this is one fundamental property of it is something we all had wrong. So moving into another sampling strategy, I think some of the new areas in transfer learning are really interesting for further analysis. So active transfer learning for adaptive sampling builds on something I'm sure you've all done, which is take data, take a model trained on one data set like A, B, C, and D here, and retrain it on a small amount of data from another data set, in this case, W, X, Y, and Z. And you can do this with less data than if you were training this model from scratch. One of the nice things about this kind of transfer learning method is that you can train it on any labels, including information about the model itself. So in this approach, we take validation data and then we put it into 2 buckets based on whether our model predicted it correctly or incorrectly. So now we have all our validation data as essentially 2 buckets, as 2 new labels, correct and incorrect. Then we can train a new output layer, just a binary classification layer, just on this binary classification task, correct or incorrect. And obviously, it's a single new layer. It's a binary classification task. There's very little, if any, hyperparameter tuning that you'll need to do on this. So it's a very simple and very quick model that you can do with not much data. Then you can apply this model to all your unlabeled data. And then across that unlabeled data, you can get a prediction. How likely is this to be correct or incorrect? So at this point, this is not that different from applying one of these uncertainty sampling metrics that we saw earlier on softmax. But where this gets interesting is how we can now make this adaptive. So we will know that, okay, here's an unlabeled item, and we think we're going to get, the model is going to get this incorrect. But we know that if we do get a human label for this item later, that once it's in the training data, we'll get that item correct because our models tend to get almost all 100% accuracy on our training data items. So even though we haven't yet had a human look at this and give it the correct label, we know that when the human later does that, this item will go from incorrect to correct in our model's predictions. So we can make that switch programmatically now, add this item to the correct bucket, and then iterate, retraining our transfer learn model, and continue to iterate to get a large sample. So this is a really interesting approach where if you have a situation where you need to get your data trained in batches and you can't have a human in the loop, quickly iterating and giving feedback, but you still want to be able to iterate on your model's updated knowledge, then this approach is a great way to do this. And this is not a particularly widely applied approach. It's in the open source code that accompanies my book. I wrote about it on the PyTorch blog about a year ago, and it's reasonably well used repo as a result, but I think it's still an area where we can have a lot of innovation in combining transfer learning and data sampling, and we're really just right at the start of that. Okay, so that was sampling data for human review. Now I'll talk about the annotation and training process and some unsolved problems there. So one, I think, really interesting area of analysis, actually jump forward a slide here, comes out of a research lab at NYU, especially in NLP recently, but I've also applied this in practical settings in computer vision. So it's task transfer learning. So it is there an adjacent task that can be annotated much faster? So in these academic papers, it's just looking at adjacent tasks in purely automated transfer learning, where there are multiple data sets that they're learning from, hence intermediate task transfer learning. So you have a pre-trained model, intermediate task, and then the target task. But I think this opens up some really interesting possibilities in terms of annotation. So in this very real use case that I saw about 2 years ago now, I was helping a company train up a semantic segmentation model, in this case in agriculture. So looking at ways of classifying weeds versus plants versus machinery, etc. And it took about 1 hour to annotate each image for full semantic segmentation. And it required a highly trained worker to do this. So this is a real bottleneck. We couldn't get many training items this way. However, it was 100 times faster and didn't require as much expertise just to label at the image level. So does this image contain a weed? Does it contain a machinery? Yes or no? So while it's not as rich as semantic segmentation, you can do this annotation over a much larger set of data, much larger and much more diverse, with less skilled workers. So it's a much more scalable process that you can roll out, only taking away from the semantic segmentation annotations pretty minimally, and if you have a fixed budget. So I think this really opens up the possibility for thinking about annotation tasks that aren't the same as the ultimate machine learning model, but are in much more efficient adjacent tasks, knowing that we can use these representations to greater effect. Finally, to focus in on annotation quality control, I think there are some really interesting recent developments in annotating subjective judgments. So sometimes if you look at the literature and annotation, it's kind of a fatalist and I think false narrative that it's not possible for people with minority but accurate judgments to be treated fairly. That's certainly true if you don't implement things properly. But one interesting approach I think we should use more in data annotation is Bayesian truth serum. So this method comes out of economics lab at MIT, and it's widely published. It's in Nature and Science journals. It hasn't made its way as much into machine learning as I think it should. And it builds on a couple of observations. The first is that if you have a power imbalance, when someone might not want to express their minority opinion because they might be penalized, you can reframe a question. So instead of asking someone what type of objective image is this, and you can see, you can have a valid subjective judgment, this was a pedestrian or a cyclist. Instead of asking only what do you think is the right answer, you can ask people, what do you think most other people would choose? Or what do you think most people would choose? And so this then licenses someone to express that they have a minority opinion, while at the same time acknowledging that it's the minority. So someone might say, well, I think 90% of people would call this pedestrian, but I think that this is a cyclist. And you're more likely to get people to provide their actual judgment, not the judgment that they think most people will want for fear of being penalized otherwise. So that's the first observation. So you're more likely to get, sometimes framed as honest, but I think that's a loaded word. Open is maybe a better way to describe it. You will get people more open about their actual judgments. The second observation is that people undervalue their own judgment. So in this example here, someone has selected pedestrian, but think that only 90% of people will agree with them. So the second part of this observation is that any judgment for which the actual annotations exceed the predicted percentage should be considered a valid annotation. And so with the full calculation of Bayesian truth serum, which I'm not sharing here, you can actually get a scenario where the highest Bayesian truth serum score for an annotator is by an annotator with a minority but valid point of view. And they'll get that higher score in cases where their point of view is underrepresented among the annotator pool. And that's actually what the worked example in my book has. So back to my introduction of this point, there are good methods out there for identifying minority but valid subjective views. And I think it's important that we look for ways to incorporate these into human-in-the-loop machine learning. So to continue the theme of interface changes to help mitigate some of the bias that we'll see in annotation, this is also true for labels of continuous values. So humans are really inconsistent in doing things like sentiment analysis on a 100-point scale. So Thames aren't the best bicycle, what's the sentiment? The same person won't even agree with themselves from one day to the next perhaps based on the items that they've seen immediately previously, so they've been primed by immediate context, or maybe they're just in a bad mood or a particularly good mood, and that could affect their score on a given day. However, humans are very consistent with themselves and more consistent across each other when you recast this as a ranking task. So which of these messages has more positive sentiment? Thames aren't the best bicycles. Thames are poor bicycles. This is much less likely to change based on immediate context or the person's mood. So simply by recasting this problem, which you can then apply a score to later once you have this full ranking, you'll get much more consistent results. One caveat is that to get the full ranking requires n log n annotations, not n annotations. However, this is a faster annotation task, so actually the total amount of work might not end up being more. So finally, I'll talk about a couple of design implications, which covers a large part of the loop here. So broadly, we can categorize annotation interfaces into these 4 different types. So unassisted annotation, as it sounds, there is no machine learning helping a person annotate data. Assisted annotation is where there is some assistance from the machine learning, but still largely human-driven. Predictive annotation starts with a machine learning prediction that a human can edit, and then adjudication is a human simply saying yes or no. And I'll go through examples of these. And as you can see here, when we think about the efficiency of the annotator, the quality of the labels that they annotate, the agency felt by the person doing the annotation, and the engineering implementation effort to implement these interfaces, there's no clear ranking here. There are pros and cons to all of these. And so the choice of which of these techniques, or which combination of them, becomes important for a given task. So let's go through an example here of span annotation. So the Ebola outbreak was first seen in San Francisco supermarket. So this is actually a task that I've done in the past, looking at disease outbreaks. So unassisted annotation is someone simply highlighting the span, San Francisco. Assisted annotation is someone clicking San Francisco, and then the machine learning model is predicting that starts at San and ends with Francisco, rather than the person needing to take a little more time to highlight that themselves. Predictive annotation starts with that item pre-highlighted, and then the annotator can edit it. This is actually, this used to be really popular in applications like e-discovery. Now it's a really dispreferred method. It doesn't align incentives between accuracy and the annotator. It can be more prone to an annotator agreeing with the machine learning prediction when it's wrong. So it can amplify some of the existing errors that already exist in the model. And it takes more time to edit something than it does to accept it. So it doesn't align incentives. The annotator is more incentivized to accept an error than to correct it. And that's not true of some of the other interfaces. Finally, adjudication is the easiest to do quality control over, and it's the fastest, but it doesn't address false negatives. So if something is not a candidate by the model in the first place, you would need other strategies in order to find those candidates. And just like with some of the other things I mentioned today, this is not a zero-sum game. You can come up with smart ways of combining these interface designs, which will mitigate a lot of the potential bias that could be introduced by having a machine learning model as part of the annotation process. So for example, if you know that your model can get close to 100% recall, but with very low precisions, there's a lot of false positives. If those precisions are around 50%, then the annotation bias from repetition prime is really minimized, because at each point, the human annotator has a 50% chance, right, of saying, yes, this is a location, no, this isn't. And so the frequency of the yes or no is not going to prime them to be biased to choosing one of those over the other. So in this particular interface scenario, you've minimized the amount of bias that a machine learning model will introduce, while at the same time get the advantages of the increase in efficiency from machine learning aided human annotation. Okay, so to summarize and open up for questions, here are 6 open questions in human-in-the-loop machine learning. 6 unsolved problems. So how does softmax base or temperature impact the rank order of items by confidence or uncertainty? So not studied in the literature. How effective can active transfer learning for adaptive sampling predict the correctness of a label before we even know what that label is? Especially useful if you have to annotate in large batches. With intermediate task transfer learning, how can you annotate a task maybe 100x more efficiently and use that task as a representation? So again, this builds off really recent academic research, and we're just starting to investigate it in practical settings. How can we use Bayesian truth serum and other related methods to identify minority but valid annotations for a subjective task? How effective is annotating continuous tasks as ranking problems instead of a continuous value problem? I think there's like one paper looking at this for just one use case so far out of University of Chicago. And how can we incorporate machine learning predictions for span annotations while minimizing bias from repetition priming? So I have demonstrated this use case in practical settings before. It has not yet been part of a peer-reviewed publication. So I think it's an interesting area for further research. All right, with that, I'll thank you for coming today, and I'll open it up for questions.
Thank you, Dr. Robert, for the insightful talk. We'll have a question and answer session. Anyone from the audience has any question for Dr. Robert? With my mind.
Sure.
So you mentioned about adjacent learning, right? That was similar to multitask learning, right? Where you're trying to, even if
Very
there's
much.
a classification problem, you have like two different things learning at the same time, and then the output is whatever classes you need to train.
That's right. So yeah, so if you have a multitask problem and you know that all of those tasks, or let's just call it two-task multitask problem, if you know that both of those tasks will be more accurate as a result of treating this as a multitask rather than separate tasks, it's essentially the same architecture. But in the case of intermediate task transfer learning out of the NYU lab, they were only trying to train one task. And they're really looking at ways in which other adjacent data sets that they can also tune a model on, which will increase the accuracy of that one task. Similar architecture though. And I'll qualify as well, like if you read those papers, you'll see a lot of the methods they tried didn't work. So this is certainly just not something you can do out of the box. This is kind of very early research stages, but I think still very interesting.
So it's more like giving more cues to the architecture, right? To be able to classify it well.
Yeah, that's right. And I think one of the most impressive things for me was that one of the intermediate tasks they were able to show improved overall accuracy was on an adjacent language. These were NLP tasks. So when it wasn't even the same language and it was kind of an adjacent task, not the same task, they were still able to show an increase in accuracy. And I think this was a big deal for NLP in general, because for a long time, computer vision models showed that something was trained on ImageNet, for example. Those representations could have a huge increase in accuracy for other applications. That wasn't true for NLP. Like language models and representations have always been popular from back in the WordDevec days. However, labeled data from other tasks has typically been problematic and has not been shown to adapt well from one domain to another. So I think it was really exciting that through some really hard and some really smart work, these researchers have finally shown this can help.
Right. And for the label data, is it like certain samples that you would go and fetch the label data with the surveys that you mentioned, like the Bayesian truth serum? Or is
so this is somewhat, the Bayesian truth serum it's somewhat independent. So you could use it with different kinds of data sampling strategies. I go into a little bit in the book about how you might actually want to specifically sample items which you predict maybe with the model of itself are more likely to have disagreement. So you could absolutely do that. But in the presentation today, this was specifically just about interface design, regardless of the sampling strategy, and how to improve that design such that people feel more comfortable expressing what they feel is a minority but valid subjective view.
So you're trying to get like more consensus. What do the majority people think, and whether this particular sample is a person belongs in a different category, right?
Yeah. I mean, yeah. Although I guess in this case, rather than reaching consensus, you're actually looking for areas of disagreement. So one of the problems can be, depending on the task, is it looks like you got consensus, but that is because the annotators know there's a majority point of view, and they'll choose that majority point of view rather than their own point of view. And there are definitely cases where you don't want that. And so, yeah, so this is more about ensuring that you get that diversity of expressions in a way that doesn't make the annotator uncomfortable or feel like they'll be penalized.
Right. Sorry. Kiran has a question. Do you think companies specialized in data labeling, such as V7 or Labelbox, are already applying active learning? And if not, why would be a blocker? Or what?
Yeah, so I mean, most are. So I was, I forget if this was in the intro, I was previously CTO of Figure Eight, the largest data labeling company here in Silicon Valley. I mean, we certainly used it. It was part of our, published products. And a lot of other companies, data labeling companies, do offer this as well. One of the reasons you won't necessarily see this in some of the outsourcing companies, like you mentioned, like V7 or Labelbox, is that sampling normally takes place upstream. So the company building the model will also come up with a sampling strategy, and the active learning has already taken place before those items go to the third-party vendor for annotation. So yeah, it's certainly part of, like, from what I've seen, the majority of sampling strategies for annotation, but for business reasons, it doesn't necessarily take place within the annotation vendor.
Yeah.
Thank you for the comment. I appreciate that. Can you share which company you're at? Right, yeah, it's Spotify are really advanced when it comes to data labeling. I think it's public. Spotify were a customer of ours when we were at Figure Eight, and we did. Yeah, it was. Your logo's on our website. We did data labeling, and I was really impressed with the kinds of tasks that Spotify had thought to annotate and come up with good instructions and do quality control for. So thank you for that compliment. I know that comes from an expert team.
For the sentiment labeling, right? Would you also recommend having a reason as well for people to say why they think, or would that matter?
Yeah, that can be really important depending on the task. And it is something I say in the book, but I don't have here. Getting feedback from annotators about certain decisions is incredibly important. Well, one of the worked examples in the end, actually, like, it explicitly flags and separately buckets anything that an annotator thinks is interesting. So that can be in the task itself, like given a reason or flagging that something is uncertain or expressing confidence, different ways of expressing feedback. And it might be in in addition or as an alternative to that, in the way that you're working with the annotation workforce. So you might have a Slack channel where they can share examples that they think are problematic, or a message board or something similar. But yeah, certainly if annotators are looking at your data, like they are going to have some of the best intuitions in your entire company about the problem that you're addressing. So finding ways for them to share their expertise, it helps your company. It's more respectful to them. It's just a win all around.
Right. Thank you so much. No more questions. Then I think we've reached the end of this talk. On behalf of TMLS and everyone here, I would like to thank you, Dr. Robert, once again. I encourage attendees to visit our partner booths and enter in some exciting giveaways.
Thank you for the invitation. It was great to be here. Oh, Kieran, I just had a question about
sorry.
I've done a lot of work with healthcare data in the past myself. Actually, a lot recently. I was helping with COVID before I recently joined Apple. Everything I spoke about today applies, and in particular, the areas around subject matter experts. Most of the time, because of sensitivity reasons, you have to work with a small number of subject matter experts for health data. Although I have seen cases where people have distributed the task into multiple tasks such that the data collectively was sensitive, but they got HIPAA approval once they separated like the first name and last name and other fields enough, such as no longer identifiable. So yeah, I think it's a good use case, and feel free to reach out to me directly, Kieran or anyone else who's on the call today. I'm happy to hear about your use cases and share my thoughts where I can.
Thanks, Dr. Robert. Yep.
Thanks for the invitation. It was great to be here, and yeah. I hope everyone enjoys the rest of the summit.
Yes, thank you. Thanks, everyone. Bye.